Just to persuade you that differential equations are really important, and that we're not just obsessed with falling objects, we did a quick trawl through some science topics to find some. It's amazing how the same equations occur in different fields. Here's just a few. Biologists, ecologists and demographers all use the Malthusian law of population growth, where the rate of change of population, p, is proportional to the population. A related version of this equation is this one from radioactivity. N is the number of a given type of nuclei present. A radioactive process changes one of these nuclei from one form to another so that N decreases. The rate of change of N, called the activity, and labelled as dN by dt on the left-hand side of the equation, is proportional to how many nuclei there are present at the time. Notice the similarities and differences between these two equations. This equation governs an oscillating mass on a spring, or any other so-called harmonic oscillator. The force on an object on a stretched spring is proportional to its displacement x from equilibrium. Minus kx is called a restoring force since it tends to restore the oscillating mass back to the centre of its motion. It's equal to mass times acceleration from Newton's second law, and the acceleration is equal to the second derivative of displacement with respect to time. Here's a second-order reaction rate law from chemistry, where the change in concentration of a reactant is proportional to the square of the concentration. The voltage across a capacitor as it discharges through a resistance is proportional to the capacitance and the resistance and the rate of change of the voltage. The rate of flow of heat transfer during heat conduction is proportional to the temperature gradient. The time-dependent Schrödinger equation is the foundation of one formulation of quantum mechanics. We've got quite a bit of work to do before we get on to quantum mechanics, so let's move on. And here's the Black-Scholes equation for the pricing of financial derivatives in economics. V is the price of a derivative as a function of time and of stock price. So what makes all these equations differential equations? Well, a differential equation is an equation that contains a rate of change, that is, a derivative. Here are 5 equations with a rate of change with respect to time. Here's an equation with a second derivative, that is a rate of change of a rate of change. Here's an equation, the first one we've seen, where there is a rate of change with respect to something other than time, in this case a temperature gradient. And in this equation we see the use of the partial symbols because the function of interest is a function of more than one variable.